A linear first-order differential equation is a fundamental concept in mathematics, particularly in calculus and differential equations. The standard form of such an equation is expressed as the derivative of y with respect to the derivative of x plus p of x times y equals q of x. Here, y is the dependent variable whose rate of change with respect to the independent variable x is influenced by the functions p of x and q of x. The function p of x acts as a coefficient for y, modifying its impact on the equation, while q of x represents an external forcing function that does not depend on y. To solve this equation, we employ an integrating factor, denoted as mu of x. The integrating factor is a crucial tool that transforms the equation into a simpler form, making it easier to solve. It is defined as mu of x equals e raised to the power integral p of x with respect to x, where e denotes the base of the natural logarithm. The purpose of the integrating factor is to eliminate the p of x times y term on the left-hand side of the equation by converting it into a product rule derivative. Once the integrating factor mu of x is determined, the next step is to multiply the entire differential equation by mu of x. This results in the modified equation mu of x times the derivative of y with respect to the derivative of x plus mu of x times p of x times y equals mu of x times q of x. The left-hand side of this equation can now be recognized as the derivative of the product mu of x times y, written as the derivative with respect to x equals mu of x times y. This transformation is made possible because the product rule for differentiation states that the derivative of the product of two functions f and g is equal to the derivative of f times g plus f times the derivative of g, where f and g are functions of x. In our case, f is equal to mu of x and g equal to y. So the derivative with respect to x times mu of x times y becomes mu of x times the derivative of y with respect to the derivative of x plus mu of x times p of x times y, with the equation now in the form the derivative with respect to x times mu of x times y equals mu of x times q of x. We proceed to integrate both sides with respect to x. The integration of the left-hand side simply giving mu of x times y, since the derivative and the integral are inverse operations. The right-hand side, integrate mu of x times q of x with respect to x requires integration of the product mu of x times q of x. This integral accounts for the accumulated effect of the function q of x scaled by the integrating factor over the range of x. The solution to the differential equation is then expressed as mu of x times y equal integral mu of x times q of x with respect to x plus c, where c is the constant of integration. This constant c arises because indefinite integration introduces an arbitrary constant, reflecting the fact that there are infinitely many antiderivatives, differing by a constant. To isolate the solution for t, we divide both sides by the integrating factor mu of x, giving y equals 1 over mu of x times integral mu of x times q of x with respect to x, plus c. This final expression provides the general solution to the linear first-order differential equation. The term 1 over mu of x effectively cancels out the integrating factor applied earlier, leaving y in terms of x, p of x, and q of x, along with the constant c. Example: solve the linear first-order differential equation. The derivative of y with respect to the derivative of x plus 2 times y equals 3x. This equation represents a relationship between the rate of change of y with respect to x and the function y itself, along with a non-homogeneous term 3 times x. First, identifying p of x and q of x. The given equation is in the standard form of a linear first-order differential equation. The derivative of y with respect to the derivative of x plus p of x times y equals q of x. Here p of x is equal to 2 is the coefficient of y, and it is a constant in this case, and q of x equals 3 times x is the function on the right side of the equation, which does not depend on y. This term represents external factors or inputs into the system modeled by the equation. Now calculating the integrating factor mu of x. The integrating factor mu of x is used to simplify the differential equation. It is calculated using mu of x equals e raised to the power integral p of x with respect to x for p of x equals 2. The integral of 2 with respect to x is 2 times x. So the integrating factor become mu of x equals e raised to the power 2x. The role of the integrating factor is to enable the equation to be rewritten in a way that the left-hand side becomes a single derivative of a product. This transformation is key to solving the equation more straightforwardly. Multiplying the original equation by mu of x gives e raised to the power 2x times the derivative of y with respect to the derivative of x plus 2 times e raised to the power 2x times y equals 3 times x e raised to the power 2x. This multiplication is crucial as it allows the terms involving y to be combined into a single derivative. Specifically, the left-hand side becomes e raised to the power 2x times the derivative of y with respect to the derivative of x plus 2 times e raised to the power 2x times y equals the derivative with respect to the derivative of x times e raised to the power 2x times y. The question may arise in our mind why this transformation is useful. The transformation into the derivative of a product, the derivative with respect to the derivative of x times e raised to the power 2x times y greatly simplifies the problem. Before the transformation, we had to deal with both the derivative of y with respect to the derivative of x and a function y separately, along with their coefficients. After applying the integrating factor, these terms combine into a single derivative, reducing the complexity of the equation and making it more amenable to direct integration. We now integrate both sides of the equation. The integral of the derivative of e raised to the power 2x times y with respect to x equals integral 3 times x times e raised to the power 2x with respect to x. On the left side, the integral of the derivative simplifies directly to e raised to the power 2x times y because integral and differentiation are inverse of each other. So the equation become e raised to the power 2x times y equals integral 3 times x times e raised to the power 2x with respect to x. To evaluate the integral, we use the method of integration by parts. integral u with respect to v equals u times v minus integral v with respect to u, where u and the derivative with respect to v are chosen parts of the integrand. For this integral we select u equals to x and the derivative with respect to v equals 3 times e raised to the power 2x with respect to x. This choice is made to simplify the integral by differentiating u and integrating the derivative with respect to v. First we compute the derivative with respect to u and v. Differentiating u equals x, we obtain the derivative with respect to u equals the derivative with respect to x. Next we integrate the derivative with respect to v equals 3 times e raised to the power 2x with respect to x to find v. The integral of 3 times e raised to the power 2x with respect to x, since the integral of e raised to the power 2x with respect to x is 1/2 e raised to the power 2x, we have v equals 3/2 e raised to the power 2x. Applying the integration by parts formula, we substitute u, the derivative with respect to u, v, and the derivative with respect to v. So the integral 3 times x e raised to the power 2x with respect to x equals 3/2 times x times e raised to the power 2x minus integral 3/2 e raised to the power 2x. With respect to x, we now focus on the remaining integral 3/2 e raised to the power 2x with respect to x. Using the fact that integral e raised to the power 2x with respect to x equals 1/2 e raised to the power 2x. So the integral 3/2 e raised to the power 2x with respect to x equals 3/4 e raised to the power 2x. Substitute this back into the integral by parts. We get 3/2 times x times e raised to the power 2x minus 3/4 e raised to the power 2x plus c, where c is the constant of integration. Thus the integral evaluates. To put the value of integral in equation 1 become e raised to the power 2x times y equals 3/2 times x times e raised to the power 2x minus 3/4 e raised to the power 2x plus c. To solve for y, we divide both sides by e raised to the power 2x. We get y equals 3/2 times x minus 3/4 plus c times e raised to the power minus 2x. The general solution to the differential equation, the derivative of y with respect to the derivative of x plus 2 times y equals 3 times x, is 3/2 times x minus 3/4 plus c times e raised to the power minus 2x.